We have the pleasure to present the mixed mode cohesive zone parameters from integrated digital image coverage only micrographs led by Jonathan. Sorry.
Thank you. So my name is Johan Hoefnagels. I'm from the Netherlands. And so this work actually, and thank you by the way for coming here. So this is actually nicely crowding up quickly, so that's good. So the whole idea is that we want to identify interface parameters, and often you don't have the access to forces. So the only thing you have is images. And I'll have a specific example in microelectronics, but you can think of anything like a bridge or whatever. So, okay. So my motivation comes from microelectronics. We look inside, there might be a delamination going on at a certain location, and there's no way that you know exactly what's the loading condition. But we can do some kind of test and see a delamination under a microscope occurring. But how do you then back out interface properties from this? Now, these look like really complex structures. So I'll show actually more a model system where we show actually that this works, the concept. But this is of course work ongoing. So we want to identify an interface model, and typically what we would like to have is a cohesive zone model, because if you identify this, then you can immediately start using it for predictive modeling. So you can change the architecture and see if delamination still takes place. So cohesive zone model, this is a numerical element that can open, and it has a traction as a function of displacement, and the area underneath corresponds to the fracture toughness. There's also another parameter that's a critical opening displacement, and that's corresponding to the peak traction. And that's typically a mixed mode parameter, because we're really interested in mixed mode delamination. So this is just an example of a cohesive zone model that we're going to be using. This has 3 parameters, and that can describe actually mixed mode delamination. But this could of course be any kind of cohesive zone element. Now, the way we want to do this is by digital image correlation, because digital image correlation gives us displacements and strains, and that's the classical way. But the way we want to use a special form of this, and this is called integrated digital image correlation. This is integrated with a numerical model. So the way it works is this is like a movie. In this case, it's just a simple double cantilever beam where we see a delamination going on here, and we get images. So we call these G. These are the deformed images. So you see it opening here, and we can compare each of these images with its reference. So this is called F. Now, if we subtract these two directly, then in a certain region of interest, then we would get a residual. So initially the residual is not so large, but when it starts opening, the residual increases. However, we know actually that the brightness goes, basically it follows the material. So if you would not do a direct subtraction, but we would subtract the brightness at the material point and subtract it, the brightness at the displaced material point in the deformed image, then this should be 0. Right? That's the whole idea of brightness conservation, but it means that we need to have the displacement field. Now the displacement field, we get it actually from a numerical simulation. And this numerical simulation depends on the material properties in these beams, but also of the cohesive zone model. That's what we want to identify. So if we get this displacement field correct, then we can subtract these 2 images and get a 0 residual. But probably we would get them wrong initially. So we get a displacement field that's not correct, and the residual is not correct, is not 0. So then we would update these parameters and start looping here until we get 0 displacement, 0 residual. So that's the DSC scheme we're using. So this is a DSC scheme where we not first get displacements or strains and then use finite element to correlate these. That would be finite element updating. In this way we directly warp back our images back to our reference. And we've shown actually in the past that this is a more robust scheme, and it makes it more sensitive to very small changes. So there's some referencings here. Okay. This is a powerful scheme. In many cases we have shown this, but in this case we really want to look at when we have something like no access to the forces. So for instance, we're looking at a microscope and we see some deformation and we see a delimitation. So we have a restricted field of view, the physical boundary conditions are not in the field of view, and so we need to apply local boundary conditions. So we can only make a numerical model of what we see basically, and have the boundary conditions basically on that kind of model of what we see. And still we don't identify it. So the presentation is mostly about how to choose these kind of boundary conditions. If we do that correctly, and then we run a numerical model with an interface model in there, we think we can be able to identify these parameters. Okay. So we're going to use a model system. So this is, of course, way simpler than a computer chip. So this is, again, this double cantilever beam specimen. And we're zooming in here. We actually do have access to the forces, but we assume we don't. So we're doing a mixed mode test here. That's basically the readers and crews mixed mode bending test. And we have a miniaturized version of this. And we do this under an optical microscope. And we get these kind of movie. And we're going to assume we just zoom in on this subregion here. Now, we're also going to do numerical modeling of this. So first we're going to do, we're going to test our framework in a virtual experiment. So we're going to just simulate the whole setup and have a cohesive zone in there, and we simulate these kind of images. As if we would have really taken these with our microscope, we generate these images like this. So this is underformed, this is deformed. And now I should say one thing. In some of the images, the crack form is coming from the right. The other images, they're coming from the left. It's just one big mess over the years. So I couldn't straighten this out anymore. So just keep that in mind. So just flip them. So in this case, it comes from the right. And here it comes again from the left. So the idea is here we build a model. Maybe you can see the mesh here. So there are two layers here and there are cohesive zone elements in between. And now the question is what kind of boundary conditions to put on this. Now the first thing you would actually think that's the most logical one is that you just take all of the edge and you prescribe the nodes. And how could you describe the nodes? Well, we could first do a global, regular digital image correlation, get displacements, and prescribe this to our numerical model. So if we do that, we have no sensitivity. That doesn't work. So there's way too much restriction actually on our boundary. So we approached this from another direction. And we said, okay, how many nodes do we actually need? So the first thing, if you have like a double clamp beam, you could say, okay, I just take 2 points and I start pulling on it. Then actually we get a big error in the displacement field. That is basically showing the error here. So because if you have 2 of them already, then you sort of like enforce the right angle, and it becomes better. It's almost 0, but you can see there's still something. 3 of them we also put in the curvature. And it becomes better. With 4 of them, then you also put in how the curvature changes with position. That should actually be enough to describe this specific test. I should say this is only for mode 1 yet. I'll go to mixed mode later. This should be enough. Then 5 is already a bit over-constrained. So when you get a bit over-constrained, what happens actually is that you identify the displacements, but there are errors in them. And they give also errors, they really can start give sort of like large errors in the numerical model. So, and I can explain more later on this. So if you have these cases 1 to 5 and we look at the residual goes nicely down and then you say, okay, there's no difference. But then here we already can see actually that for 5, in terms of the relative errors of the identification, it starts going up again. So it's really like smart thinking of how much do we need actually to prescribe the right boundaries. So the local boundary conditions, when you don't have force, is really to capture the kinematics accurately. So how what's actually going on, but we shouldn't do too much. So we should really have sufficiently unconstrained regions. So if we really constrain all these boundaries on the top and bottom side, then it goes wrong. And then on Monday, actually, I showed that if you then start including these boundaries as a degree of freedom, then you can have more boundaries. Okay. Now we try this. This is actually from experimental results, and then we did an experiment, and we give a different kind of initial guess before our interface model, and then we can see that it correlates very nicely to values that we would expect actually. Okay. Now we go to mixed mode because it becomes more interesting. So in mixed mode, now this is flipped again. Now the crack is coming from the right. So if you think, okay, how do we actually, well, what do we need to enforce? Now we also need to have the shear in there. So we do need to add additional degrees of freedom on both sides. And the crack is actually running completely through this. So the process zone is actually larger than this region. Yeah, okay. And you basically get these kind of more complex deformations. So in order to get this correctly at each point here, as you can see, we need more of these boundary nodes in order to exactly prescribe actually the true deformation state in this beam. First, we do a virtual experiment, and from that we can actually learn a bit on how this works. And Xi here is actually a parameter in our test where we can change the mode mixity. It's from the Readers and Cruise test. And then what you can see is actually that over these tractions, the stress actually here is 0. It goes up to sort of like a peak, and then it goes down again. So that's the red lines. So this is for a test that's close to mode 1. This is close to mode 2, and this is intermediate. But what's interesting, the blue ones, is the angle. So you can see that even though this test was designed actually to be constant mode mixity, the mode mixity changes rapidly. So while you go from right to left, basically the angle is rotating over which is being pulled. Now you could say, oh wow, that's a really big complication. But actually we looked at this, okay, that's nice, because there's a lot of information in there, we can use this. This would mean that we basically, if you look at sort of like this process zone, then it's sort of like this intermediate test here, we would basically probe all of the different angles. So one test should be enough. And actually, to identify the best test for this, there's a lot of tools. So sensitivity field, we can do an eigenvalue decomposition of the Hessian matrix. I don't want to go in detail, but there's a paper on this if you're interested. So you can really identify beforehand what is the best test to do so. Now, if we do this, now still virtually, we created a virtual test, and now we're trying to identify without using the force to get the three cohesive zone parameters. So this is the starting residual fields at different times. So you can see that the model is quite off, and in time you can see that the residual is going down, and all the three parameters actually are converging. And the mixed mode parameters is the least sensitive, and that's what we already would predict beforehand. But then we go to a residual field that's really very nice in the end. So this works. So we can have identification of mixed mode cohesive zone parameters from a single mixed mode test using micrographs only. And this could also be photographs of a bridge. So like, this is just conceptual, we're testing this, but if you're working on a different system, right? And then going back on the different tests, so like the mode 1, and this is really the mode 2. So in the mode 1, actually, you can use it very well to identify, this is the errors on these parameters. The errors on the mode 1 parameters are very low, but it gives a large error on the mixed mode parameter. But even we can still identify something, because the mode 1 test is actually not really a mode 1 test. We did earlier, we were identifying a mode 1 model, but this was really wrong, we found out later. It was just, there's a lot of mixity in there. So, okay, we can debate about the Readers and Cruise test. But anyway, if we take this intermediate test, then you can see that we have errors that are less than 1%. At this moment, still only virtual. But then, and then we see if we give different initial guesses. So this is the space of the three parameters, and then they all converge nicely to one point. So it's a very robust system. As long as you have these boundary conditions cracked, then it just very robustly converges. Now, okay. Now, finally, almost to the end. Now the real experiments. We did these real force displacement curves here. Now you can see actually that already at this mode mixity parameter of 0.63 actually that there's this is basically catastrophic failure, so it shoots through the image. So then there's nothing to there's no information there. So so the 0.5 now is like this, but you can already see it becomes a bit unstable. So it's not as good as we predicted numerically. So from that we say, okay, let's be a bit on the safe side. Oh wait a minute. Sorry, wait a minute. The green one is this. Sorry. This one doesn't do any delamination. The 0.5 is the unstable one, and so we use this 0.25 in this case. We also can actually, in mode 1, we can just look at the area under the curve and have a fracture toughness. So we can compare with that. And that's, well, in this case, 44 for this particular specimen. And then the idea again is, can we have a single test that to identify this, and we're using this test now at a slightly lower mode mixity, but still knowing that actually inside the process zone there's all this mode mixity in there. We do this, now this is experimentally, this is at the initial gas, we have again these residuals, and then we converge. Now it's not completely zero, and it's probably due to the fact that the model that we're using is not really the actual model of not perfectly capturing what's happening in the interface. That's also why why now basically this test, the 0.5 is basically unstable, while in our numerical predictions that should be correct. But still we're coming close, right? So this means that basically the interface model is doing something correct. So it's describing it quite close. And so we can have identification here, and if you now have different initial gases, it does converge. There is some variability, but it converges. So let's look at these numbers. So we get these numbers. So this is the mode 1 fracture toughness, mode 1 critical displacement, and the mode mixity parameter. So the first one you get from the mode 1 test, and this agrees with the experimental uncertainty. The second one is very hard to know, but if you look at the interface, we use this model system with a glue layer, and so a critical displacement, something like the 7 micrometers, corresponds to a failure displacement of something like 50 micrometers or something, or maybe somewhere between, let's say, 30 and 100 micrometers, and that's what we see. So we see these, so that corresponds, and then finally, we have a mixed mode parameter of 3.3, so that means that the fracture toughness increases a factor of 3.3 when you go from mode 1 to mode 2. That seems also plausible. So this seems to work. So that's the end. So far we of course worked only on this sort of like model system, but it seems to work. So if we identify what we really need in terms of these boundary conditions, but we still leave enough freedom that the material can deform, such that if we change the material parameters, that there's actually some change in the deformation field, then we can be very accurate in identification. So we need to leave sufficiently unconstrained region. Then I didn't have time, of course, to go all the details, but there's a lot within this framework. There's a lot of tools to analyze actually what's going on. So we did this virtual experiments, then everything works perfect. That's always like that. We did real experiments, and we are also pleased actually. It took a lot of learning, a steep learning curve, but now and a lot of these lessons learned are in this the second paper and also there. Thank you for your attention.
Probably we can put some questions upon questions.
I have a lot of questions. It was very interesting.
Thank you.
First of all, I got confused between your C and your zeta. If you went...
Okay, yeah.
No, I thought zeta, I thought you said that C was between 0 and 1. That's what
Yeah. So okay, so okay, that's the point. I stepped over this too quickly. In the Readers and Cruz mixed mode bending test, they introduce a parameter called Xi, which is basically it's basically an where is this? Oh, now I need to. Oh, it's very slow. So here,
C's the length, isn't it?
C is this position basically. If you pull on this side, on this structure, you do a mode 1 test. If you pull on this side, you actually do an end knot flexure test. But if you pull somewhere here, I think probably where the mode selector is here, then you do a mode 2 test. So you go from mode 1 to mode 2, you can tune how you're loading the specimen. That's C. That's how you do the experiment. Zeta is an interface parameter. So it's an interface parameter explaining the mode mixity. So it's how much larger the fracture toughness in mode 2 is compared to mode 1. And that's the well, I also didn't invent the parameter zeta for that. That's coming from the cohesive zone, the typical type of Van der Bos. That's previous from my group developed a cohesive zone model, and it had it had 3 parameters. So fracture toughness in mode 1, the critical opening displacement, and also the zeta parameter. So that's really on the modeling side. So here you can see it. So these cohesive zones that are in there, the cohesive zone elements, they basically have 3 of these parameters. There's a formulation in there how the traction and the opening, how they go, but also this changes when the angle under which the interface is being loaded, then this area increases with the factor 3.5 when this is loaded. Now it's loaded in mode 1. But if you load this in mode 2, then this goes up a factor of 3.5. If zeta is 3 or 3.5, 3.3.
Because GC will depend on the mode mixing.
Yeah. So it basically, instead of having you're right. It's a whole curve. It's a whole curve, but it's sort of like approximated by just one value and a second value. It would have been. You're right. It would have been better if I would have said here GC1, GC2. It would have been clear, I guess. Even though that's not what we're identifying, because the model uses internally uses a zeta parameter, the exact formulation matters in terms of what kind of sensitivity you get. Actually, that's why I didn't do that. But in terms of clarity for this presentation, I can see how that's better.
Because GC is a GC of zeta.
Yeah.
GC of zeta.
Yeah, and then this,
zeta.
and this is GC1.
GC1.
And this is zeta is sort of like the ratio of GC2 to the GC1.
Okay. And what was your material? Because you're showing a material 1 and material 2 schematically.
Okay, sorry, this is very schematically, yeah. Actually, somebody asked me yesterday, and I was thinking, we did a lot of tests on molding compound epoxies with copper lead frames. That's encapsulation. But actually, these tests later on we did on just 2 steel plates with a glue that's being used in the aircraft industry. So it's.
So is it cohesive or adhesive?
It's the fracture is a cohesive.
It runs within the layer.
Yeah.
Glue?
Yeah. So but we also did test on the completely other material system. It also works. They weren't as convincing and stuff like that. So it basically we're just testing the framework, right? And trying to.
Steel up there.
Yeah, there's the steel layer, another steel layer, and the glue in between. And that's so it's a bit far away from the computer chip. So we're trying to merge that. The idea is, by the way, that we would take a computer chip from the conveyor, like from the manufacturing, and they would see a crack, and we would take one from the production line, and remove the material and look at the cross section, and then start doing a test, and then really see what I showed earlier, that you see the eliminations going on, and we identify the interface parameters from that, and then update then the model can immediately be used to update the architecture. So that's where we got the funding from Philips from. We're a bit far from that. Oh, Bamber, yeah.
About halfway through the presentation, you showed some traction curves for different mixed mode ratios.
Yeah.
And I think for the lower mode mixities, they showed distinct peaks, and then for the higher mode mixity, I think it was 70%, it was sort of flat.
Yeah, what that means is that basically we never reached the stable crack growth regime, which is not because basically everything was process zone there. So it starts to basically, if you're just initially, the process zone builds up, and you want, typically for this such a test like this, you would like to have a process zone that is stable and moves along. But we really don't need it actually, because we can also identify when we just have a process zone that becomes bigger and bigger and bigger, and you never see the end of it. That's fine, but it's not optimal.
Do you need a larger region of interest for the high mode too?
No, because I didn't really mention this so much, but our region of interest is smaller than the process zone. It's like you're just looking here, but the crack is coming by. So initially, in the first time frames, you see the initial part of the crack, and then, while the crack is going down, you take multiple images, and we're correlating all of the images at the same time. So all of that data is in there. It's just not in there in one frame. It's just, yeah, it's in there. And that's why we can use the data's in there, so we can correlate with it.
So this would be okay for something which has a really large damping zone, like an adhesive or something?
Yeah. That's basically the case we're looking at. We're looking at the case where the process, we have positive identification, also for case that the 0.7 case, where really the crack is just developing, and we just look at a portion of it, but it's not optimal, because you would like to have in your field of view like all of the different mode mixities in there, so all of the information, in order to get the good sensitivity to the mixed mode random.
Okay, thank you.
Thank you.
Congratulations by your intensive work.